here's a mind-bending truth that will completely change how you think about earthquakes. Nearly 9 out of every 10 units of energy released during these devastating natural disasters never actually contributes to the ground-shaking destruction we witness and fear. When we imagine earthquakes, our minds immediately conjure images of violently swaying buildings, cracking pavement, and the terrifying sensation of solid ground buckling beneath our feet. But here's where it gets controversial. What if everything you thought you knew about earthquake energy was fundamentally wrong? A groundbreaking study published in AGU Advances has revealed findings that challenge our basic understanding of seismic events. Through an innovative series of laboratory experiments, researchers have uncovered the shocking reality of where earthquake energy actually goes. And the results might make you question everything you've learned about these natural phenomena. The research team accomplished something remarkable by creating what they call lab quakes, essentially miniature earthquakes generated under carefully controlled laboratory conditions. Think of these as earthquake simulators that allow scientists to peer inside the physics of seismic events in ways that would be impossible with real-world earthquakes. These controlled experiments provided researchers with what they describe as a complete energy budget for earthquake-like events, offering unprecedented insights into the mechanics of ground ruptures. Here's the part that most people miss, and it's absolutely staggering. Only approximately 10% of an earthquake's total energy actually produces the physical shaking that causes buildings to collapse and triggers the devastation we associate with seismic disasters. So where does the remaining 90% disappear to? The answer might surprise you. The overwhelming majority of earthquake energy, anywhere from 68% to an astounding 98%, gets converted into heat around the earthquake's epicenter. This means that while we're focused on the dramatic surface effects, the vast majority of the energy is essentially cooking the rock deep underground. Even more fascinating is that less than 1% of the total energy goes toward actually fracturing rock and creating new geological surfaces. Matej Pech, the study's co-author and a geophysicist at MIT, emphasized the significance of these findings. Our experiments offer an integrated approach that provides one of the most complete views of the physics of earthquake-like ruptures in rocks to date. This will provide clues on how to improve our current earthquake models and natural hazard mitigation. But here's where the methodology gets really interesting. The research team didn't just randomly create their miniature disasters. They meticulously designed their experiments to mirror real-world conditions. They used granite samples specifically chosen to replicate the seismogenic layer, which is the crucial section of Earth's crust where most earthquakes originate. The goal was to simulate the incredibly complex microphysical processes that occur when rocky layers suddenly slip along fault zones during actual seismic events. The experimental process itself was fascinatingly complex. Researchers ground granite into fine powder and mixed it with magnetic particles. But these weren't just random additives. The magnetic particles served as sophisticated temperature markers, allowing the team to track heat generation throughout their artificial earthquakes. They then subjected these samples to steadily increasing pressure conditions that carefully replicated the natural stress conditions that exist deep underground before real earthquakes occur. And this is where the story takes another unexpected turn. The researchers discovered that the energy distribution wasn't consistent across all experiments. Instead, they found that the energy budget varied significantly based on what they termed a region's deformation history, essentially the geological memory stored within the rock itself. Daniel Ortega Arroyo, the study's lead author and graduate student, explained this concept in remarkably accessible terms. That history affects a lot of the material properties in the rock, and it dictates to some degree how it is going to slip. In other words, rocks remember their past stresses and traumas, And this geological memory directly influences how they'll behave during future seismic events. Now, here comes the controversial part that's likely to spark heated debates among geologists and seismologists. The research team boldly claims that their tiny laboratory earthquakes accurately mirror the physics of massive, real-world seismic events. Critics might argue that this is an oversimplification. After all, how can a small lab experiment truly capture the incredible complexity of tectonic plates grinding against each other hundreds of miles below the surface? The researchers acknowledge this limitation, but maintain their position. They argue that while the real world is undeniably more complex, their experiments successfully characterize the core physical processes that drive seismic activity. Peck admits, "We could never reproduce the complexity of the Earth, so we have to isolate the physics of what is happening in these lab quakes. We hope to understand these processes and try to extrapolate them to nature." The implications of this research extend far beyond academic curiosity. These findings could revolutionize how we approach earthquake prediction and disaster preparedness. The study demonstrates what researchers call a viable method to bypass the spatial and temporal limitations of our current seismological tools and geological observations. In practical terms, this means we might finally have a way to study earthquake physics without waiting for actual disasters to occur, or trying to interpret limited data from seismometers scattered across the globe. Moreover, these insights could dramatically improve our ability to identify regions most vulnerable to future earthquakes. If we can better understand how geological history influences earthquake behavior, we might be able to create more accurate risk assessments for different areas. But here's the question that should keep us all thinking. If 90% of earthquake energy is invisible to us, generating heat deep underground while only 10% creates the destruction we experience, what does this mean for our current earthquake preparedness strategies? Are we focusing our attention and resources on the right aspects of seismic risk? This research forces us to confront an uncomfortable reality. We might be fundamentally misunderstanding the very nature of earthquakes. And if that's true, how many other facts about natural disasters might need complete revision? What do you think? Does this research change your perspective on earthquake science? Or are you skeptical about extrapolating laboratory results to real-world geological events? Should we be investing more resources in understanding the hidden 90% of earthquake energy? Or is the 10% that causes surface damage still the most important focus for public safety? Share your thoughts. This is exactly the kind of scientific discovery that deserves passionate debate.